Hi everybody, welcome to Multirate Signal Processing, today about artificial neural networks. The so-called convolutional neural networks are a special kind of neural network, and they are like cascaded filter banks, but with a nonlinear function at the output of each filter and a constant offset. See for instance this link here about deep learning tutorial. Its coefficients are called weights in this context, so it's a different field and they have different terms for the same thing. So this is important to keep in mind. The so-called artificial neural networks simply use a weighted sum instead of the convolution. So this is the general type of neural networks, and the convolutional neural networks, they use this sum and shift it over the signal like a correlation or a convolution. So you can also read more about it in this Wikipedia link here. And also I can recommend our project workshop webpage where we have this topic in more detail and also with many Python examples. And this is based on the book from Eugene Charniak, Introduction to Deep Learning, from MIT Press in 2018. Yeah, and a nice example for image understanding can be seen here in this link from Karpathy, where basically deep learning is used to try to gain information about content of images. Yeah, so actually those applications are quite impressive. So both types, general neural networks and convolutional neural networks, use several layers of cascading. So in filter banks we basically have one layer. A filter bank is one layer here in this context. If there are more than 3 layers, they are called deep neural networks with deep learning. So this learning corresponds to the so-called training process, which is the same as optimization, as we will see. These are current active research areas, for instance for speech recognition and image recognition, as in the example above. A popular example is the so-called MNIST handwritten digit recognition, described for instance here in this link about machine learning mastery. So this example, as most neural network implementation, uses Python and its library Keras. Another library is Python PyTorch. So MNIST is basically the hello world of neural networks, where you have a data set of handwritten digits, and the goal of the neural network is to recognize the handwritten digit. So this is the hello world because it's an open source data set which is available for free on the internet, and also it's limited in scope. It just has 10 different digits and the network has to recognize which digit it is. Yeah, so the nonlinear function f of x, also called activation function, is often the so-called sigmoid function. Right, here you can read more about the sigmoid function, and this is defined as this function, 1 over 1 plus e to the minus x. So you can see if x is large, then this term disappears and the result is 1. If x is very small or negative, it's a large negative number, then e becomes very large and then this expression goes to 0. So for large negative x it's 0, for large positive x it becomes 1. Yeah, so we can also plot it with IPython. So here when we start IPython, we can create an x-axis, say from -6 to +6 in steps of 0.1, and then we plot the corresponding function values here, and then use the plot function to plot x and epsilon, and we get the resulting sigmoid function, which you can see here. So we can see at -6 it's already quite close to 0, and then here around 0 we get the function value 0.5, and then it saturates towards +1. So it's basically like a limiting function. So it behaves like a soft limiter function. And we can also get a closed form derivative of it. Here is the derivative of it, right? And this derivative, again, is important for applying optimization, or in this context called training. An often used alternative activation function is tanh, or ReLU, short for rectified linear unit, which returns x if x is larger than 0 and alpha times x if x is smaller than 0. So this is a simpler function, and it turns out often this is actually giving better results. tanh is also a sort of soft limiter. It's just not between 0 and 1, but -1 and 1. And depending on your application, it might give you better results. And you can see what kind of activation functions are available in this web page for Keras, or in this web page for PyTorch. So there are actually many more nonlinearities or activation functions. So those activation functions are important, for instance, for recognition purposes. So if you say, I recognized a digit, then the corresponding neuron or output of the filter should be, say, close to 1, and if it's not recognizing it, it should be close to 0. And it doesn't really matter if it's like large, much larger than 1 or 1, it's always recognizing, or same for 0. It doesn't really matter if it's like large negative or 0. So that's why those soft limiters make sense. And here's an example of a 3-layer artificial neural network. So here you have your input layer, where you have your signal consisting of the samples of x, so x0, x1, x2. So this might be, for instance, the pixel of your image containing the written digit, right? Or it could also be the samples from an audio signal appearing here at the input. Then we have weights. So here you can see W, H for hidden, and 0 means from sample input number 1 to hidden node 0. So you have weights to the different hidden nodes. So each node can be seen, for instance, as a filter containing those weights. So then we have several of those nodes or filters. And then the next layer is doing basically the same thing. It has weights now from the hidden layer output to the output layer here called O, O0, O1, and so on. We have different outputs. So you could imagine each output being, for instance, a detector for a certain digit. So if we have those 10 digits, then we would have 10 outputs for the digits from 0 to 9. And each is for detecting its corresponding digit. For instance, here the first output would recognize the digit number 0. And then we would apply this nonlinearity, for instance, the sigmoid function to the output, such that it is between 0 and 1. And 0 meaning not recognized, 1 meaning recognized, and say 0.9 meaning recognized with a probability of 0.9, for instance. So the output can be written as the weighted sum of the hidden layer and then we apply this nonlinearity, for instance, this sigmoid function. And this nonlinearity is also usually applied to the hidden layer output. So in turn, this hidden layer output is obtained by computing the weighted sum of the inputs, followed by this nonlinear function, for instance, the sigmoid. Right, so here we have the definition of the sigmoid again. Yeah, and the values with index 0 of those inputs are often assumed to be the biases. So for the bias we have a fixed value, for instance 1, and then we have this weight which corresponds then to the exact value of the bias, and this is then learned or optimized too. So again, it depends on the application if you want to have this bias or not. So in the case of recognition of patterns like the digits, this bias makes sense because then we could implement, or the system could learn a thresholding. So if the output of, say, some hidden layer is above a threshold, then it recognizes a certain value or a certain property, and it basically is turned on, and if it's below this threshold, it's turned off. Yeah, so in general we have several outputs in our neural network. Output k is the nonlinear function of a sum SOK, right? O for output and k for number k. So here again we have our weighted sum, we apply our function to it, and we obtain the output k. Yeah, so the sum is the weighted sum from the hidden layer outputs hj. And we choose x0 or x0 equals h0 equals 1 for the bias, such that we also obtain a constant offset as part of the sum. So in this way, mathematically, we combine the bias with the inputs. As you can see here, it's one unified sum in this way. Yeah, the output of the hidden layer, hj, is again a nonlinear function f of a sum, shj, right? So the same form of the computation for the hidden layer. The hidden layer sum is the weighted sum of the input values x. So here you can see it, we have this weighted sum. X was our inputs. Here we have the weights from the input to our hidden layer, and here is our weighted sum for the hidden layer sh and j. And then again we apply our nonlinearity to it. The output of our neural network then depends on the weights w and the inputs x. We assume a fixed sigmoid function here. We assemble the inputs in the vector x. So that's better. So here we have our vector then. That makes it easier to write mathematically. And a vector w, which contains all the weights from the hidden and the output layer. So here we just collect all the weights in our neural network in this vector w here. So now we can express this dependency. We can rewrite the output k as O, the output of number k, which depends on the vector x of our input, for instance, the pixels of our digit image or the samples of our audio signal. And it also depends on the weights of the network which we learn. So after the optimization or training of the network, the w will be fixed, and then x will be the input. So for our training or the optimization, x will be given by the training set, and w is to be obtained by the optimization or training for a desired output OK. So now we would like to train the network, meaning we would like to determine the weights w, such that if we present the neural network with a training pattern in x, the output produces a desired value. For instance, if you present an image with an object in it, the output indicates that the object was there with the desired output value. So for instance, the output, the corresponding output, OK, would have a 1 or a value close to 1. Hence we have training inputs and desired outputs, dk. Right? And for neural networks, this is also called the target. The desired output is called the target. So that's another term specific for neural networks. We now use optimization to update the weights W to obtain outputs OK as close as possible to the desired outputs or target dk with a given input x. Right, so here for the training process, x is given from the training set. dk is also given, the desired output, because for the training set we know which digit they represent, for instance. So we have a set of training images which contain known digits, and we can present the network, the inputs, and the desired outputs. And then we train the weights such that the desired outputs are obtained as close as possible. And for that we use the gradient descent from last time. So last time we knew that we can obtain gradient descent update from just computing the gradient for a certain data point. Right? We have a gradient at a certain point, and this point represents a certain set of weights, W, and then we get the update for the dates according to this gradient. Yeah, for this gradient descent, we need an error function, right, which tells us how close we are to the desired output. So this is our error function here. It consists of the obtained output for a given training set and a given weight set W minus the desired output. So the obtained output minus the desired output is our error function, and this error function should be close to 0. To make it a positive function, to make it always positive, we simply square it. So we take this error function, square it such that we can apply minimization. Right? For gradient descent, remember we get the minimum, and we cannot apply it directly to this difference because then it would become negative. And that's why we square it to obtain a positive error function. Right? And this we can minimize now. So if we minimize this error function, we get a number which is as close as possible to 0. Right, and we take this 1/2 squared because it's convenient to optimize. And this is also called a loss function for neural networks. So in neural networks, the objective function for optimization is also called the loss function. Yeah, and this particular choice is the mean squared error here for the kth output. So that's why we still have this k. We could also have a weighted sum of the squared errors of all the outputs, but for simplicity we just look at this one output k. Yeah, so to this error or loss function we can now apply the gradient descent, which we saw in equation 1 of the last lecture, number 15. So here you can see it again. We get the new x updated as an update from the old x, and here we have the update term minus alpha times the gradient at the old point x. And in our case now this x becomes the w, the weight, right? The weight is what we want to optimize. So in our case of neural network training, it is also called stochastic gradient descent, or short SGD, since we often apply it not to the entire set of training signals, right, like all of our handwritten digits, but we do it sequentially to different subsets or batches of it. So that has the advantage of that we just need to load a certain subset, because often the training set is really large and we cannot really load it all into memory at once. So we do it sequentially in batches. And it also has the advantage that this makes it more robust against overfitting. So this gives the gradient a certain unsharpness or noisiness, and this avoids overfitting to the target. Because our goal is that it also works for examples which are not seen in the training set but are just similar to it, right? And this stochastic gradient descent then also helps in this respect. Yeah, so this is our update equation for our neural network now. So you can see here we update the weights. So the new weight vector becomes the old vector updated by alpha times the gradient with respect to the weights. And this is the gradient for the output k. Right, so here we have it for network weights w and output k. For the gradient nabla, we need to compute the derivative of the loss function, which here we call r, with respect to each weight wi of the weight vector w. In our case, we can apply the chain rule, which is the outer derivative times the inner derivative. So remember, the ERR consisted of squaring of the difference times 1/2, which you can see here. So this squaring would be a function of that we apply the outer derivative to. So first we have to take the derivative with respect to the square function here. So we get 2 times delta, and then we can see conveniently the 1/2 cancels with a 2. So what's left is just the delta, which you can see on the next row, times the inner derivative, which is the derivative of the delta with respect to weight I. And the delta, remember, was just the output for the kth node minus the desired output for the kth node. And the desired output is fixed. So the derivative of something fixed becomes 0. So what's left is then just the derivative of the output of the kth output, the kth node. Right. So this looks, again, quite convenient. So this is the difference of the obtained and the desired. And this is the derivative of the output with respect to w, to wi. So we compute this inner derivative first for the last layer of the output weights for output k. So here we have the weights which produce the output, ok. And we again apply the chain rule, now applied to equation 1 above, or to ok equals f of the weighted sum, which is our activation function f, the sigmoid, applied to the weighted sum of input as ok. So here the outer derivative is with respect to this nonlinearity f, which is our sigmoid function, and then the inner derivative is with respect to our weighted sum. Yeah, so here we can see it. Our derivative of the output with respect to each of the weights is then here the outer derivative. You can see f prime is the derivative of our sigmoid function times the inner derivative, which means the derivative of the weighted sum. And here you can see in the next row the weighted sum. And if we take the derivative with one of the weights here, then all what's left of this sum is this particular term where this weight appeared. And what's left then is just this vector, the corresponding vector factor for this weight. So in that case it would be just hj here, which appears here. So then what's left is simply the outer derivative of the sigmoid function times hj. So that looks a lot more simple now. So now we can take this result here, this result 4, and plug it into our equations 3 and 2 above for our gradient descent, and obtain the update rule for the gradient descent for the output weights. So here you can see it. We have the updated weights for the output layer is the old weights minus some factor alpha times the difference between the output and the desired times the derivative of our sigmoid function at that point times the weight that goes to this output. Yeah, so this basically is a very simple rule. It says the weights update. Here, this piece is alpha times the output delta. So this is the output delta, the difference between obtained and desired, times output derivative. Here, the derivative of the sigmoid function times its input hj. So here, this is the corresponding input to this output node. Yeah. So this is basically a local processing for the update. So we just look what's the difference for the output, then what derivative do we have at this point, this operating point of this output node, and what's the corresponding value that comes from the hidden node to the output for this weight, for weight j, right? And then we have this update. Yeah, and since this is only local processing, this makes it suitable for massively parallel processing, for instance in graphics processing units or GPU. So we can update all the weights in parallel using this update rule. Yeah, so for the hidden weights from input I to hidden node j, the inner derivative of equation 3 becomes a little bit more complicated, since we now get derivatives for it from each output OK. Right, so basically this is where we get the so-called backpropagation. So here we have an output difference, right? And this difference is easy to compute for the output layer. But then for the hidden layer, we don't have the desired values. So we have to come up with something equivalent to this difference for the hidden layers. Right? And this is what it makes it a little bit more complicated. But it's doable again with a chain rule. So here we can see it. Again, I apply the chain rule now. Now I take the derivative with respect to the hidden weights, WR and WH, as you can see here, and apply that to the output nodes, and apply the chain rule here. So here we take the output again, which is this nonlinearity function of the weighted sum. So again, outer derivative times the inner derivative. So again, this is the weighted sum. Here we have the weighted sum again. And here we have the derivative with respect to the hidden weight. And the hidden weight appears in hj, right? So we have the hidden weights, which corresponds to node j, hidden node j. So that's why we only keep one term of this sum, the j's term. And what's left is then, instead of just the factor hj, now we need to take the derivative of this output of the hidden layer hj with respect to the weight in this hidden layer. So remember, for the output layer, basically we stopped at this point because it was just hj. Here we have now to continue with the derivative. So the output of the hidden layer or the hidden node hj is again this nonlinearity f of this weighted sum, and we can again apply the chain rule. Here we have in the next row the derivative of our sigmoid function at this operating point of the hidden layer times the inner derivative, which is this weighted sum. And again, this weighted sum only has one of those weights which affect the output here, which affects the derivative, and that's basically the xi here. So finally we just have this result here. So here, outer derivative for the output layer, for the operating point of the output layer, times the weight which connects the output layer, the corresponding output layer, with one of the hidden layers, times the derivative of the sigmoid function at this operating point of this hidden layer, times the input value of this hidden layer. Right. So now we can plug this result for the hidden weights, number 5 here, again into equation 3 and equation 2 for the gradient update, and obtain the update rule for the gradient descent for the hidden weights. So here you can see it. So here's the update. The new values for the weights of the hidden layer are the old weights minus alpha times delta of x and w. So this is again the output delta times f prime of our sigmoid function here, of our output weighted sum, times the weights which connect the output with the hidden layer, and times the derivative of the sigmoid function with respect to the operating point of the hidden layer times the input. Right, so this is now our update here. And observe that we get separate update terms for each output index k. Right, so when we look at it, we have still the k in here because we have k different outputs. So actually we get k terms which basically accumulate for the update of the hidden weights. So we would go through the outputs and then accumulate the weight updates in this way. Yeah, so we can actually simplify this update equation if we define a new backpropagated delta term from each output index k as this. Right, so we have this output delta times this derivative times the weights which connect the output layer with the hidden layer, and in this way now we have a new backpropagated delta. Remember, at the output we easily obtained this output delta by taking the difference between the obtained and the desired, and now we compute something similar for the hidden layer. Remember, for the hidden layer we don't have it directly, but now we compute something which approximates it, right? Which is this output delta times this derivative times the weight, right? And this is our backpropagated delta, and that's actually where the term backpropagation comes from. We take the output delta and we backpropagate it. And this is a very common form of training for neural networks, this so-called backpropagation. And here we can see, and I just show, that backpropagation is basically nothing else than gradient descent. Backpropagation is an example of gradient descent applied to neural networks. Yeah, and this says, again, the update of our weights is alpha times backpropagated delta, this term here, this term, times derivative of the hidden function here times its input x. So it's basically the same update rule as before, just applied to the hidden layer with a backpropagated delta. Yeah, observe that this accumulates the backpropagated deltas from the outputs, and this algorithm is the so-called backpropagation because of this nature. Yeah, so this is in principle the same rule as for the output nodes, as I just mentioned, just with its corresponding input and output. So again, local processing and parallel processing, which is important for fast implementation. Yeah, and this means backpropagation is just a consequence of applying the gradient descent algorithm to neural networks. A popular alternative to or refinement of gradient descent in neural networks is the algorithm ADAM. See also this link for Keras and also this link for PyTorch. So actually recently I prefer PyTorch because it seems to work better. For instance, you can easily have print commands inside your models, which you cannot have with Keras. And especially for large networks, for debugging, this is actually really helpful. Yeah, so hence for all nodes we obtain a local processing, as I just mentioned. We just look at one node, call its input xy, its output o, its weights wi, and its desired output d. Then we obtain its output with this equation, the weighted sum, and then we apply the nonlinearity to it. And if it is an output node, the difference delta to the desired d is then this equation, simply the difference. And if it is a hidden node, we use the backpropagated delta from an output difference do, a weight to the output node wo, and a sum for the output node so. So then we get this result. So the backpropagated delta is simply the output difference do times the derivative at this point times the weight which connects the output node to this hidden node. Yeah, and then we get the local weight update in any case as this. So the new w is the old w minus alpha times this delta times the derivative of our nonlinearity, or at this operating point, times the corresponding input to this node. And this is also depicted in this diagram here. So we have one node, which is the weighted sum including the nonlinearity. Here the inputs. Here we have the weighted sum followed by this nonlinearity. And this is then the weight update during training with this output difference delta. So here this is then this local update. Very convenient. So here's a Python example for the MNIST digit recognition using Keras. So here I have a Keras example, and I also have a PyTorch example. As I mentioned recently, I'm preferring PyTorch. So I can open this one here, show how it looks like when you program it. So I open the editor, gedit, my MNIST example from PyTorch, and here you can see how it looks like. So here it imports Torch and Torch Vision. Torch you can install not using PIP, but going to their website, and in the website, in the PyTorch website, you can actually see instructions on how to install it. More to it in a moment. So here you can see how a neural network is defined in PyTorch. So here I call this class DenseNet, and it's based on this class module. Right, so you have this class definition, and the first function that you defined within this class is the init, which basically assigns the network initial weights. And you can see here it derives this initialization from the DenseNet module function here. It takes this init, and here you can see it defines the structure. Here you can see layer 1. It's a sequential network consisting of a linear layer, which is the weighted sum. Basically, this linear implements the weighted sum. Here the input dimension is the number of pixels that we have in our images. Right? We just take all the pixels, make them one vector. So basically we unwrap our picture to make it one-dimensional, and that's our one-dimensional input. So remember, for this linear layer, it doesn't really matter what dimension the input is. Right? We just have a number of inputs and weights, and then we sum them up. And that's why this always is one-dimensional here. The output is giving the number of pixels again here, so we don't reduce the dimensionality in this case. We keep the dimensionally intact. This is our hidden layer then. And then we have the output layer, which is again a linear layer, which takes the output from the hidden layer, same dimension here, and the output layer now has as many outputs as we have a number of classes, and the number of classes is 10 in our case. So here you can see it down here, it's the constant, and I define it as 10 because we have 10 possible digits. Here I'm also defining the training set size, so I'm taking 100 images for training, and then I take a different set of 10 images for testing to see how good it is in generalizing from the training set to previously unseen images. And that's the crucial part here for the training. We don't want the network just to work on the training set. The most important part is that it also works on unseen examples. Yeah, so here we have our two layers, and then we need to connect them here with a forward function, which we can see here. Here we have the definition of the input. So when we execute it, we actually execute this forward function. Here in the init, we just initialize everything, the structure and the weights. Here, this is used for computing an output. So here we have the first layer applied to the input x, get some output, again x, it's overwritten. Then here we have a second layer, again an x, and then we just return the x. And we also see here the nonlinearity which we have between the two layers. So here in this case we use the ReLU function. Remember, the ReLU function is basically just cutting the negative values to 0 or very small values. And the positive values remain unchanged. So a very simple nonlinearity here. It just suppresses negative outputs. And then the second layer here actually has no nonlinearity in this case. So really simple. So here we could also try softmax, for instance, as a nonlinearity, which is sort of turning the output into a probability distribution such that the outputs sum up to 1. Yeah, so here I define it. Then here I'm setting our constants, and here I'm now loading the data from MNIST. So here I have this data loader, and it downloads the data set. Right here for the training set, and here for the test set. And you can see here as part of the downloading, it also applies a transform for the normalization, for instance, here. Right. And it also converts the data type to PyTorch tensor. Same for both types. Yeah, so here I'm then going on, which basically sets the batch for training. So X is the images, Y is the target, the desired output, which is basically the true digit. So here this function then generates this training set, And here we can see what's in it. Right here, the type, X-train type, Y-train type. So here we can see X is a type of image, and Y is integers between 0 and 9. Yeah. So here we have it for the type, and here we can see the shape. So we can see how many of them we have, or the shape of our input. Here this is the image shape, and here you can see how many desired digits we have for the target. Yeah, next I plot a few example images from the training set. So each time we run it, we get some random subset here. So we will also get different numbers. And you can see I keep a test image unflattened because I will flatten the rest. Remember, we have a one-dimensional input which we need for our network. Right, so here we flatten the images. So here X-train. So here we take the shape here of the number of rows and the number of pixels, and we now flatten it using the view, using number of pixels here. So here this is the total number of pixels in an image, and this will then appear in a row of X-train, so that we have just a one-dimensional vector here for X-train and X-test. Yeah, and after preparing now our data set, basically turning our images into PyTorch tensors which have just one dimension, we set up the model. So here model now becomes a denseNet. So here now this becomes this class denseNet, and this model now contains our neural network initialized with some random weight values. Right, and here you can see the total number of parameters which is present in this model. So this is basically the total number of weights which this is printing. So this looks a little bit cryptic, but this just gives you the total number of weights. Then we need to define the loss function. So remember, I mentioned the mean squared error. So here the mean squared error doesn't really make much sense because you just want to have a correct output. And it doesn't really matter if the correct output is a 0.9 or 1.0. It just has to be the correct output, and for that you usually take the cross entropy loss. So this is an information theoretic loss function which basically looks at the probability density function that is obtained from the neural network. It treats the 10 outputs from the neural network, which are between 0 and 1, and treats it as a probability distribution. And then it compares this probability distribution with a desired one, which has a probability of 1 at the true output and a probability of 0 at the other outputs, and applies the cross entropy to it. So that's an information theoretical function which tells you how different two distributions are in bits usually. And so this is a suitable loss function in this case, because if both are identical, then you have 0 bits difference. If they are different, then you have more than 0 bit difference. So basically this is the number of bits you need to describe one from the other, or the number of bits which represent the entropy going from one to the other. Yeah, then I need to define our optimizer, which we apply for the training. Here I'm choosing the ADAM. Input is the model parameters, the weights. And then I'm choosing just some starting point here. Here I'm setting a start time, and then I have a for loop using just 10 iterations for our optimization. And you can see here's the starting point for each loop. It takes the input, the training input, the current model, and the output of the current model. Then it computes the loss function for the current model, for the current predicted y, compared with a desired y. So these are the digits, or rather the probability distributions that it obtains. Then here it prints the loss, and then here it does the update. Right, here you can see it sets the gradient to 0, and then this is the backpropagation step, where basically it's doing the backpropagation that we just saw. And here it's doing the update of the weights. The optimizer step is then doing the weight updates. Yeah, and after 10 iterations it's usually done. It prints the duration by computing end time minus start time, and here it's doing the testing. So here now it applies the obtained optimized model, the trained model, now to the test. Right, this is one digit which is not in the training set, and it tells me what digit it should be. Here I'm computing the loss, so again it outputs the probability distribution. Here it compares the true with obtained probability distribution with this loss function. Here it saves the obtained weights if you want to use it somewhere else. And here it shows the test image. Right, I'm using the non-flattened test image plotted in grayscale, and then you can compare it with the output, which I'm doing here. So ypred is model of sample. So here, remember, this is the probability distribution. So here we get pred, and here this is the prediction, which basically takes the largest output. So we just choose the output which has the highest probability, which makes sense, right? If we have, say, an output which is 0.6 and the rest is lower, then 0.6 is the most likely output, which is then the output is then the argument which has this output. So that's why I'm taking the argmax here. So this is the prediction. So this is the digit which it predicts. So now I can let it run. So Python 3. So here you can see the example images, 3377. So you can see the handwriting is sometimes actually not so easy to recognize, even for humans. Then we have the training. So you can see the training loss goes down, starting with 2, and then it ends up at 0.1. And you see it's just 10 iterations, and the loss went down a lot. And now here's the test set. Here we have the test image, which is not part of the training set here. It shows a 9, but it says it's a 4. Well, when you look at it, it could actually be also a 4. It's not so clear maybe, but it's most likely a misclassification. Right? So that actually is something that easily happens. Here we also need to take into account that the training was rather short. So I could also increase the training, saying go to 100. Let's see if it works better with 100. So here you can see now we have different examples in the training set. And now it has 100 iterations. Here is now the test set. Shows a 0, and indeed it classified it as a 0. And here you can also see the output of our neural network. So since this is not normalized, remember I didn't apply this softmax. The softmax function is actually applied inside the cross entropy loss function. That's why I don't need to apply it in the neural network. But here the largest number here, 13, is indeed for number 0, right? So the argument here is 0, so we get digit number 0, and the rest is much smaller. And also when you look at the loss function for the training, you can see it became tiny, right? So for the training set at least, it does a very good job, because the loss function became really tiny. So that worked. So that shows you testing is important, because it shows how general a neural network becomes. And also enough training is important for accuracy, to get sufficient accuracy. Okay, so this was a dense or linear neural network, or linear layer. The next case is convolutional neural network. So in convolutional neural networks, each layer basically consists of filter banks where fixed bias terms are added to each output, and the result is passed through a nonlinearity. The filters are also called receptive fields, in analogy to the processing, for instance, in the retina of the eye, or filter kernel, in analogy to image processing. The filter coefficients and bias terms are then optimized according to a target function and a loss function, which computes the distance to the target function. So basically as before. So here's a Python Keras convolutional neural network example. So most neural network development is done in Python. It has powerful libraries for it, for instance Keras and Theano or TensorFlow. Right? Python Keras and Theano are libraries to compute and train neural networks, which you can also find here. So sometimes Keras and Theano are easier if you are a beginner for simple networks, but I found, as I mentioned, PyTorch for larger networks more convenient, because you can use the print function, for instance. Yeah, so to install Keras and Theano, this is actually quite easy. We simply go to a terminal, a Linux terminal shell, and type these commands: sudo pip3 install Keras and sudo pip3 install Theano. So Keras by default runs with TensorFlow. If you want to run it with Theano, which is another front end, you simply edit this file here, which is in your home directory. And this is also a difference to PyTorch. PyTorch is not building on another library. It's actually standalone. So you would use PyTorch instead of TensorFlow or instead of Theano. So that also makes it a little bit easier to handle, because then you don't need to update all those different libraries in Symfony. It's easier to maintain just one library, in this case PyTorch. Yeah, so in this file, you simply replace TensorFlow by Theano to run it with Theano. You can also install this Python 3.h5py, which can be used for store the weights. In our example, we will want to detect a signal in a sequence. Here in our example, a ramp function, simply the numbers from 0 to 4, using a convolutional neural network. In the Keras example program, here, this example program, we first define the input, the data, and the desired output, the target. So for the input, we prepend and append a few zeros to the ramp function, which we want to detect, such that the neural network has to find it. It has to find the position of the ramp. So here's our simple input. So in the beginning, you have 9 zeros, then you have your ramp function, which also starts with a 0, and then in the end you have again 9 zeros. So then the goal is to simply detect this signal and the position. So basically like a matched filter. We need to add we need to expand dimension because Keras expects x with a certain shape. So here we just made a one-dimensional signal, could be some audio signal for instance, but Keras expects a three-dimensional tensor with dimension badge. Remember, we have different badges for the training. Then the length of our signal, so this would be actually the dimension of our signal. And then we have this additional dimension channels, which can be used for instance for stereo or for RGB channels in images, for color images. So in our case it's really simple because we just have one badge, this one X, and we also just have one channel. So all what's left is basically this length dimension. Here we have length 23, and we just need to add two empty dimensions in this case. And the target signal has the same size in this case, and this is because the causal network, we use causal convolution here, returns the same number of samples at the output as the input. So again, that's something that's convenient. We set it up as containing all zeros except for a 1 at the time of detecting the pattern. So that's our desired output. Here y is our desired output. Here initialized with 23 zeros, the size of the output. And just at one position where we want to detect the signal, we want to have a 1 from the network. Right? That's the desired output. And that's slightly different from a matched filter. Remember, for a matched filter, we just want to have a maximum output at the time of detection. And at the other time points, we don't really care for the outputs. Here, we just want to have the output at the precise location of the detected signal and 0 everywhere else. So that's different. Here, this is actually beneficial for precisely detecting the location of our signal to detect. For matched filters, we want to maximize the detection and don't care so much about the precise timing. Right? So the goal here is actually slightly different from matched filters. Again, we need to expand the dimensions. Right? We need to append the channels dimension here. The badges dimension. Right here we already have 2 dimensions, and we transpose it here so that we already have dimension 16,0 at the end, and then here we add a dimension, we add the first dimension as an empty dimension. So then we set it up. So maybe I should make this appear at the same indent. Yep, that looks better. So then we can set up this neural network as a sequential neural network. And here we now add our convolutional one-dimensional layer to it. Here this is conv1d layer. Since we have a one-dimensional signal, this is suitable. And here you can also see it how Keras is doing it. Basically it starts with initializing with an empty sequential network, and then it adds layers to it. Here this convolutional one-dimensional network, which has one filter, right, which is for the detection. This is our kernel size. This has the size of our signal, so 8 weights or 8 coefficients. Strides equals 1, which means we have in normal correlation or convolution no downsampling. So basically we have a downsampling factor of 1. Strides is also a term which is used for neural networks, and this corresponds to the term downsampling in multirate signal processing. Right? Again, some term which is different in different fields, but it has the same meaning. Padding, which means we the way we add zeros for the convolution to the beginning or the end. Here we have the case causal, which means we add as many zeros to the beginning such that we have the same output samples, number of output samples as input samples. Activation function is our nonlinearity. Here we don't want to have nonlinearity, so we just choose linear. Right, so basically just like a filter. Use bias, so that's the bias term which we are not using here, so we have no offset. Then we have a kernel initializer, which is the weight initialization with random numbers. So here this is the type of random numbers it uses for the initialization. And here is the input shape which it expects, so this is the size of the input. So that's basically it. Yeah, so basically this sets up a filter, a linear filter with no bias of size 8 and no downsampling. Yeah, so the filter here is used to detect a pattern similar to a matched filter in our lecture Advanced Digital Signal Processing, slides 13, for instance, on our website. The kernel size is the size of our filter's impulse response. Here it can detect patterns of length 8 samples. So as I mentioned, strides equals 1 means that there is no downsampling. Padding equals causal means there is 0 padding of kernel size minus 1 zeros before the beginning of our signal. Activation equals 0 means there is no nonlinearity after the summation. Use bias equals false means the bias is 0. Kernel initializer is the random initialization of the weights at the beginning of the training, and input shape is the size of the signal at the layer's input. Yeah, so in Keras we then need to compile the model and specify the used error function and optimizer. So what we just did in Python separately, here we do it with this compile function. So here you can see it. Here we specify the loss. So in this case we want to have the mean absolute error, which is simply the mean of magnitude of the difference between obtained and the target. And again the optimizer is ADAM. Yeah, so again the loss is the error function. Here the mean absolute error between network output and the target. Optimizer is the optimization function to use to obtain the best weights. Here ADAM, which seems to be the best. So now we can train it. So here the training, instead of using this for loop, is simply done with this model fit function. So it's in Keras it's a little bit more simple. You can see it, but it also means that you have less flexibility. For instance, if you don't want to do something extra in the optimization loop. So here it runs for 5,000 epochs. So that means this for loop goes over 5,000 iterations. Batch size is 1, since we just have this one training sample, and here we have X, the training input, and Y, the desired output. Right, X is the data or signal, Y is the target, and epochs is the number of iterations. And batch size, the number of training batches. Okay, so after the optimization finished, we can use our model for prediction. Here detecting the signal, usually a separate test signal is used, which differs from the training signal as we just did for the digits. But here we take the same for simplicity. So we just want to see the principle. So here, after we're done, we use model.predict. So that's how it's done in Keras. X is the input and we get predictions. And we can also read out the resulting weights with model get weights. So then W contains the weights. So the first index of the weights refers to the layer, and here we only have 1, hence the index is only 0. Then the next index refers to the input dimension. the next to the output dimension. So we have only one output neuron, hence the index there is 0. And finally we have the channel's index, again 0. So hence our filter weights have this form here. So here we get the 0 for the first layer. Then here we have the weights of this first layer. Then we have batch 0 and channel 0. So this then shows us the weights such that we can plot it. We can also save the weights, for instance, in a pickle file using these commands with open name of the pickle file, write binary as weight file, pickle dump ww in the weight file. So pickle is a convenient way to store structured data from Python, not just for neural networks, but basically any structure. Using pickle has the advantage that we can more easily analyze and modify the weights if we wish, compared to model save weights. So this is another possibility. And this would store it in a compressed way. When you have large models, this is actually important to compress them, because otherwise it becomes too large. Yeah, so we can now plot the output of the neural network, the weights and the input. The output and the weights have the same format as the input, batch length channels. In our case, the first and the last index is 0. So here we can now plot it. Here the predictions. You can see it's in the middle dimension. So here first was the batch, last was the channel. Then the same for the weights, which we read out before, and here finally the input signal, which has the same format. Yeah, now we can use this file here. First I open it. Basically you then can see it's exactly what we just saw. Gedit. So here it is. And here you can see I'm using the Keras modules. And the first function here is generating my dummy data, my example data, and here you can see is my example input, this RAM function in the middle of zeros. Then here I'm doing the formatting for Keras, getting the right dimensions. And here I'm creating the target function with the 1 at the right position. And then I'm returning the 2. Here I'm generating the model, as we just saw, starting with an empty sequential model, and then I'm adding one layer here of this one-dimensional convolutional layer with the correct setup. Here I'm doing the compilation with the desired loss function and the desired optimizer, and then I'm returning the model. So then I can call it in the main loop here. First I generate my dummy data, the x and training x and target y. Here I'm setting up my model. So model contains now my model. Here I'm doing the training with the function fit using 5000 epochs. And here I'm doing the evaluation. I'm testing it with x and y. And here I'm doing the prediction. Right, here I'm seeing what we get, and here I'm also doing the extraction of the weights, show the weights, and then save the weights, and finally plot the prediction and the weights. Yeah, so you can see it's actually fairly simple, and you can see what it does. Python 3. So here it's running the optimization. You can see it actually takes a while to get those 5000 iterations done. And here you can see the result. So here was the last epoch, and this last line comes actually from this model evaluation. It just basically gives us the last state of the optimization. And here you can see the predictions. that we get for our input signal. So you can see here it actually indeed comes quite close to the desired output. It's mostly 0 or very small. You can see it, and the largest value here is this. So this is actually very close to 1, 0.99999, right? So this is the desired one, and then we have a few small values before and after. So you can see actually the error is rather small. And it's really peaky because the values right next to it are really small. So this is good for detection and finding the precise position. And here you have the corresponding weights, and they are actually easier to see here in the plots. So here's the input signal, the ramp. You can see here at position x equals 14 it ends. So here are the weights from the network. You can see it actually looks quite different from the input signal, and that's also different from matched filters, right? For a matched filter, remember, the weights would be the time reversed input signal, but here it actually looks quite different, and that's because the desired output is like this. So here at sample number 16 we have a precise detection, right? And before and after we have just small numbers. So that's also different from a matched filter where the neighboring values would also be large. So the goal is somewhat different. Yeah, and you can see it worked, right? So we indeed have a working solution for our system. So this is something you couldn't do with matched filters, and for matched filters we have a closed form solution because of the formulation of maximizing the signal to noise ratio at the time of detection. But finding a closed form solution for the desired target value that we prescribed here is actually not so easy, and that's why optimizing it worked quite fine in this case, right? For optimization we can get solution where it's not so easy to find a closed form solution, or even impossible. And impossible is particularly the case for large networks. Yeah, so these are the network outputs that we just saw. So that shows it works, right? Yeah, so as I just mentioned, it's quite different from a matched filter because it has a different goal. It maximizes the signal to noise ratio. Yeah, so in the matched filter case, the weights should be the signal to detect but time reversed, here a reversed ramp function. But our weights function looks quite different. This is because we specified a target function which only has a very narrow peak, and this is what you also observe at the output of our convolutional neural network. This may not have a maximum signal to noise ratio, but a more narrow peak at detection, which enables a more precise location of our pattern, so precise timing location. Yeah, so we could also choose padding equals valid in our convolutional neural layer. So remember we chose causal, and we can also use valid, right? And this is the default, but then no zero padding of kernel size -1 zeros before the signal starts is done, and hence the output of the convolutional layer will be accordingly shorter than the input. But we can obtain the same results if we remove accordingly kernel size -1 or filter length -1 samples from the beginning of the target function with this, right? We have defined this gap value, which is filter length -1, and then we just modify our target function by starting later. So this compensates for the missing zero padding in the beginning. So this is a trick to deal with it. Just remember that the output is accordingly shorter. Kernel size -1 samples in the beginning are missing compared to padding equals causal. And then we can let it run it with Python 3 Keras simple convnet valid.py. So this is basically the same now with valid. So let me try it. Copy. and paste. So now it runs same as before, 5,000 iterations. And you can see here, this is the input signal, same length. Here we have the weights, they basically look the same, right? So basically we have the same result, but now we can see the output is shorter, right? It only has like 15 samples here because it is correspondingly shorter because of the convolution now not doing any zero padding in the beginning, right? Okay, so this is basically a trick to deal with the different setups of the convolutional layer.